download folders. For those of you joining us on webcast, please type your questions into the window by the webcast. We have an administrator monitoring questions in that thread who will ask your questions. And for those in the room, please note that we have a microphone. Please wait for the microphone so folks on the webcast can hear you. Our speakers are Jeremy Mathis. He's the director of the Arctic Research Program in NOAA's Climate Program Office. Xiangdong Zhang is a professor at the International Arctic Research Center and Department of Atmospheric Sciences. And Igor Polyakov is a professor with a joint appointment at UAF's International Arctic Research Center and College of Natural Science and Mathematics. We'll start with you, Igor. Thank you.
I'm Igor Polyakov. I'm professor with the International Arctic Research Center and Department of Atmospheric Sciences of the University of Alaska Fairbanks. My educational background is in oceanography and climate change. I'm with the University of Alaska for 20 plus years already, so I'm a veteran of Alaskan studies now. And I would like to start with my presentation with some time series which illustrates the anomalous state of the Arctic Ocean. My educational background is oceanography, even though I have some contribution to climate studies in general and linkages between climate change in the Arctic and North Atlantic regions. So this two time series show instrumental records derived for the Atlantic water temperature, the upper panel, and freshwater content of the Arctic Ocean. Again, these are observational time series. They cover multi-decadal period of time. As you can see, the Atlantic water temperature starts with Nansen observations in 1893 and continues to the very recent years. And the freshwater content time series starts from 1920. And ends in recent years. So these are observation-based instrumental records. And the Atlantic water temperature is about the intermediate water layer in the Arctic. The Arctic Ocean may be seen as a sandwich with a very warm layer in the middle, in the center, separated from ice by very cold, fresh, stable layer. If this layer would be removed, the Atlantic water carries so much heat that ice would disappear in a year. And the amount of heat carried by this Atlantic water layer is enough to melt several ice covers of the Arctic. So it's an enormous amount of heat. And you can see a lot of variability in this time series, but in the last decade, the peak is enormous. And that tells us that the Arctic Ocean is at its very extreme state. So the Arctic Ocean in general is very warm. No precedent in the history of instrumental observations lasting for more than a century. As for the freshwater content, the change is even more drastic. In last decade, you see that red anomaly signifying freshening is just enormous. There is a lot of fresh water associated with ice melt, associated with additional river runoff flow, and Xiangdong will probably comment on this. He's an expert in this area. So we see a lot of changes in the Arctic Ocean. I'm leading scientist of big observational program in the Arctic Ocean, and in recent decade or so we conducted many cruises in the high latitude Arctic, and we definitely observed features which were not observed in the past. Arctic Ocean became dynamic, became just wild with changes occurring in the central basin. For example, last year we were in the high Arctic and we were not able to find a suitable ice flow with our big icebreaker to deploy buoys. That was the first time in the history of our observations lasting for more than 15 years. So just no good ice flow in the Arctic. That's a big logistical challenge. And these are just several examples of changes occurring in the Arctic Ocean. So there were several publications stating that we are now probably not in extreme state, but in a new state. It's not already an extreme state, but just a new state of Arctic climate. And we have impacts of these changes in the Arctic Ocean on all components of the Arctic climate system. This next slide. So you see changes in the Arctic Ocean are shown schematically in the center. There are several colors, several circles in this blue big circle, identifying the contribution of different forces in changes in the Arctic. So they are due to ice melt, they are due to dynamics, they are due to freshening, and several others. And all these components influence differently on other components of the Arctic climate system. So these changes of impacts on other climate system components are shown by big circles surrounding the central one. So we definitely see impact of Arctic Ocean on atmosphere, on terrestrial component, on, of course, human beings, and all these components are clear, but the prediction of these changes sometimes difficult to make. So this is a complexity of our system, with numerous feedbacks, with numerous changes which are not easy to monitor. And probably my colleagues will comment on this later. Thank you.
Thank you. Next up is Dr. Zhang.
Okay, thank you. So my name is Xiangdong Zhang. I'm from International Arctic Research Center, and also I have a joint department with the Department of Atmosphere Science. Today I would like to share some new findings from our data analysis. So I would like to start with the temperature changes. So during the last several months, the global mean surface air temperature reached record high. So when we look at the, could you move to the next slide? Okay. When we look at the temperature anomaly during the last 3 months, we found that there is a dramatic increase of surface air temperature over the Arctic. So this is also record high surface air temperature. It makes a strongest contribution to the global mean temperature increase and the record high during the last several months. We try to understand what caused this dramatic increase of temperature just within one season. So when we look at the weather pattern, when we look at the atmosphere circulation pattern, so we found in last December, there was one superstorm moving into the Arctic. Just one storm increased surface temperature in the center of Arctic for 7 degrees. Yeah, just 1 or 2 days increased temperature for 7 degrees. So we also look at the mean, seasonal mean sea level pressure is a representation of atmosphere circulation. So we found that we can see the blue color extended from North Atlantic side into the center of Arctic. That means there's more storms coming into the Arctic, Central Arctic. That's also intensified the Siberian high moving northward. We can see there's red color over there on the upper right panel. That means the high pressure is very strong over there. So that creates larger pressure gradient. So that means that there is a strong wind blowing from North Atlantic into Arctic that transport moisture, transport heat into the Arctic. Actually, when compare this temperature pattern and the sea level pressure pattern with the Simpson in 2006, 2007, we found it's quite similar. So I'm not sure if we still remember what happened in 2007. That's a record low sea ice, right? So we already got the increased temperature in this winter. So what may happen for sea ice in the coming summer? So could you move to the next slide? So let's track the changes of sea ice curve in 2007 or before 2007 to look at when this weather pattern occur. So what happened for the sea ice curve? Maybe your push button is like elevation. Okay, we can see the same weather pattern occur in March 2003. We got a decrease of sea ice curve over the Barents Sea and the Kara Sea. Move to next slide. Next one. Yeah. Okay. The same pattern occurred in March 2005. So we got a further decrease of sea ice. So further, when we look at the March 2007, so there's a dramatic decrease of sea ice on North Atlantic side. That's a record low of sea ice curve, winter record low sea ice curve in 2007. Okay. Following this change, following this track of sea ice changes. So if the atmosphere circulation pattern or weather pattern will vary following the same way in 2007, we may expect the record low of summer, record low sea ice curve during this coming summer. So could you move to the next slide? Yeah, we can see in 2007 summer, there is a record low sea ice. But right now, there's a low sea ice curve over the Barents Sea and the Kara Sea. So if the pattern continue the similar or the same as what happened in 2007, we may got other record of sea ice curve in this coming summer. So we are continue studying this, so working on this by using data analysis and model experiments. Let's see what happens. Okay, good. So next, this explains why there is, it's an explains the mechanism why there is a decrease, dramatic decrease of sea ice curve on the Barents Sea side, the North Atlantic side. We can see when that weather pattern occur, there's an increased atmosphere heat transport from North Atlantic side going to the central Arctic. That means provide extra heat to the Arctic that can help melt sea ice. Actually, Igor already talked about the ocean. So I did not include the ocean figure here, but when we look at the wind stress, that's wind stress forces the ocean currents. We can see wind blows from North Atlantic side into the Arctic, right? That means that can enhance power ocean warm water going to the Arctic. So when combined together from the atmosphere and the ocean, that can accelerate the sea ice melting. Yeah. Okay, go to next slide. So just now I talked about the temperature increase, the sea ice decrease. Right now I'm trying to show the other recent finding. It's about the wetting trend over the Arctic. So we published a paper together in the Nature Climate Change. So from the panel showing the bottom, so during the last 50 years, so we found that there is largely increased water transport in the atmosphere. That means there's more water in the atmosphere going to the North Arctic and the northern high latitude. So those water can come from the lower latitude through evaporation, ocean evaporation. So at the same time, we also found that there is dramatically increase of river discharge. Yeah, river discharge contributes to the ocean freshwater, can change the ocean circulation, and also can change upper ocean stratification, and then further impact the sea ice melting and the growth. So other interesting thing is that we found that there is a record high of water transport in the atmosphere in 2006. There's also record high river discharge in 2007. So that's extreme climate events. Okay, next slide. Go further. So this is like a mechanism. Okay, this is from this slide. I would like to show you a new finding. You know, when temperature increase in over both the ocean and the land, so sea ice got melts, right? Snow also melts. So what's the relationship between them? Because the land got warmer earlier than the ocean, so that means the snow retreat earlier. There's a phase difference of a seasonal cycle. Right? So we found that if there's an early retreat, early melt of a land snow, that can trigger changes of atmosphere circulation over weather pattern, and then further influence the impact the falling summer surface air temperature over the Arctic to cause a further warmer surface air temperature over the Arctic, and then further decrease of the sea ice over the Arctic, showing in the bottom panel on the right hand side. Yeah, that's the information I would like to share with you guys. Yeah, thank you.
All right, thank you. Next up is Jeremy Mathis.
Thank you very much, and good afternoon, everybody. I don't have slides to show. I thought we would probably be saturated on PowerPoint at this point. So I do want to talk about ocean acidification, because along with being the director of NOAA's Arctic Research Program, I'm also the founding director of the Ocean Acidification Research Center here at the University of Alaska Fairbanks, and I'm continuing to coordinate the ocean acidification research network and monitoring activities that are going on in the Arctic Ocean and around Alaska. And for the journalists that are sitting in the room, I know that I think I've spoken with all of you at some point over the years about our ocean acidification research and the pace at which ocean acidification is happening in the Arctic. And unfortunately, that wasn't something that was really highlighted during the last week as we listened to a number of talks and attended a lot of sessions. We only really had one specific talk that focused on ocean acidification. And that's really alarming because, as I said, ocean acidification is progressing faster in the Arctic than really anywhere else on the planet. And it's driven by a few things. Number one, the water is still very cold in the Arctic, and cold water can hold more carbon dioxide. And ultimately, that's what's driving ocean acidification, is the uptake of carbon dioxide that's been emitted from human activities into the ocean that's causing this increase in the ocean acidification around the regions of Alaska. So because the oceans around Alaska are cold, they're naturally preconditioned to have lower pH, to be more acidic, and to have lower saturation states for important carbonate minerals that are used from everything from crabs to clams to little small animals that live in the ocean that make up the base of the food web. So we discovered about 10 years ago now that this very rapid progression of ocean acidification was happening in the Gulf of Alaska, in the Bering Sea, and in the Arctic Ocean proper. And so we started a very extensive monitoring network where we used a number of different vehicles and platforms to measure the change, whether we were going out on ships or whether we were putting moorings in the water, or now using unmanned vehicles that can go out and map large regions over the course of several months. And so we find more and more that ocean acidification around the state of Alaska and in the Arctic is outpacing the changes that are occurring around the rest of the planet. And that's really alarming, given the reliance that the state of Alaska has on seafood and the fishing industry. So last year we published a study that showed that the state of Alaska in itself is vulnerable to ocean acidification, but there are certain regions, particularly southeast Alaska and southwest Alaska, that have an especially high risk associated with ocean acidification, really because of the reliance on both the commercial fishery and the subsistence fishery that exist in those locations. So as we go forward and as we build out Arctic monitoring networks and we sustain our observations in the Arctic, which has been a big theme that we've heard throughout the week, is a need to invest and sustain Arctic observing networks. We need to make sure that we remember ocean acidification as a primary driver both from a science standpoint, but also from a policy standpoint, to help us support and keep those monitoring and observation systems out in the ocean, so that we can serve not only our Alaska residents and our Alaska stakeholders, but also inform the global community, because the changes that are occurring in the Arctic, especially due to ocean acidification, will also happen in the rest of the world's ocean. So it's a great indicator for not only how the water chemistry will change, but also how ecosystems could respond to that change. So I'll stop there and turn it over to Tom.
All right, thank you for those comments. We also have Tom Ravens, who is the Associate Dean for Research and a Professor of Civil Engineering in the University of Alaska Anchorage College of Engineering. Thank you, Tom.
Thank you. Turn your slides so I can see them. So, good afternoon. So I'm going to talk about climate change and its impacts on Arctic coastal erosion in Alaska. And the short story is coastal erosion is accelerating in the Arctic and in Alaska. And that is directly associated with the warming. Coastal erosion in an Arctic setting is particularly vulnerable to erosion because not only are mechanical processes important, but also thermal processes. So, for example, when it warms in the Arctic, you have reduced sea ice. That generates larger extent of open water, giving rise to larger waves. The warming is leading to greater open water periods every year, so therefore the coasts are exposed to the erosive powers of waves and currents for a longer time every year. Subsidence is happening, the lowering of the land surface at the same time sea level is rising. That's in general raising ocean levels, causing more of the land surface to be acted on by erosive waves and currents. And then finally, coastal permafrost thaw is another ingredient to the accelerating coastal erosion associated with warming. And one way to think about it is that the north coast of Alaska is essentially a large ice cube, and it's 70% ice by volume, which is really a remarkable thought, really. And as the environment warms, well, that ice cube is thawing at an accelerating rate. So we've been focusing on coastal erosion and coastal processes at two locations on the north slope of Alaska. One of them is Drew Point, and the other is Barter Island. And that area between Drew Point and Cape Halkett, which you see in the figure there, is experiencing some of the highest rates of coastal erosion in North America, as much as 10 to 20 meters per year, which is just almost mind-boggling. And this particular area is particularly vulnerable to erosion on account of the, once again, the high ice content of the bluffs, again, 70% ice by volume, but also because the solid material in the bluffs is fine sediments, silt and clays, and when erosion happens, those fine materials are readily dispersed. There's nothing left behind to sort of slow future erosion. Barter Island, which is another site that we've worked on, sees a lot lower rates of erosion, and that's because there are, even though the ice content is pretty high, there's a lot of coarse material. So we're starting to understand why erosion rates are higher in some places than in another, even though generally rates are accelerating. So I was just take a minute to talk specifically about coastal erosion at Drew Point. There, coastal erosion proceeds via a process referred to as niche erosion block collapse. There's a cartoon in the upper right. Basically, there's typically a small beach before the bluff, And during a storm surge, the water levels rise, allowing contact between the water and waves and the base of the bluff. And the waves thermally and mechanically cut a niche into the bluff, undermining it. And then that leads to block collapse. And then that fallen block is thermally and mechanically eroded by waves and currents. So that's just a conceptual model. We've developed a numerical model based on those processes, and we've calibrated that model with an earlier time period and validated it with a later time period. And we've actually been able to develop accurate predictive models of coastal erosion in certain locations in Alaska, and that's something to build on. Next slide. But although not all parts of Alaska are seeing 10 to 20 meters per year of erosion, a lot of places are vulnerable, and in particular, communities on the west coast of Alaska, like Shishmaref, as you can see in that photo there. Historically, when the fall storms rolled in across the Bering Sea, there was ice in the sea, which provided a buffer, protected those communities from the waves and storm surges. But nowadays, with the ice gone, there's nothing to protect these communities, and so they're getting whacked really bad by these storms. But it's not just the West Coast communities that are seeing increasing erosion. Even Cook Inlet sees increased coastal erosion. So, for example, Point Warrenzoff in Anchorage sees increasing erosion, and that's because the ice that forms along the coast and protects it in the wintertime is only present for a shorter, well, it is present for a shorter and shorter period of time every year. So for a longer period, every year it's exposed to waves and currents and erosion. So it sounds like it's all pretty bleak, but there's actually some interesting ideas that we've been, I think that we've been exploring, which provide, perhaps in some cases, a protection against erosion in Arctic environments. And that is the idea of deploying thermal siphons or similar systems to basically supercool the coastal permafrost. And our preliminary calculations indicate that it would be feasible to cool the permafrost sufficiently with these systems, or perhaps even more active systems, in order to slow the rates of coastal erosion in sort of high-value infrastructure areas. So those are my remarks. Thank you.
All right. Thank you, and thank you all the panelists. We'll take questions now if anyone has any.
Hi there, Matt Miller from KTOO in Juneau, and this question is directed to Jeremy Mathis. And I talked to one of your lead researchers, who's sitting right in front of me here, the other day at length about some of the effects of ocean acidification. I wonder if you can kind of put a little bit of a point on it for perhaps the commercial fishing industry in Alaska. At what point are the levels going to be such that some of the species in the Bering Sea, the Chukchi Sea, and the Beaufort Sea, when are they going to be no longer viable, and when is the fishing industry going to start seeing some potential effects to, like their catches, and what kind of species are we talking about here, and what are people going to see in what they do catch?
So thanks for that question, Matt, because it's a really good one. Unfortunately, we don't have an answer to it yet, which is why it's extraordinarily important that we keep doing the monitoring work that's going on right now. So we've done a fairly good job in the past few years of constraining the ocean environment, figuring out how quickly the water chemistry is changing because of ocean acidification. The piece that we're still missing gets to the heart of your question, which is how the species are going to respond, how the commercially important species like a crab are going to do under these new conditions that we're observing. But equally as important are how the lower food web is going to respond, which has a cascading effect up to things like a salmon, which it may not be directly impacted by ocean acidification, but if its food source is disrupted, that could have negative consequences for that fishery. So those studies and that research is still in its infancy right now of understanding how the ecosystems and specific species are responding to the new ocean conditions that we're seeing with our observations. So we hope over the next 5 or 10 years to be able to provide a really good forecast for how each fishery and each region is going to respond to ocean acidification, so that we can tell the fishermen what they need to know and how they need to plan in order to deal with any potential disruptions. Because to date, we haven't seen an impact in a commercial fishery or otherwise because of ocean acidification. We just know that the potential exists for those things to possibly occur. So it's vitally important that we continue our monitoring efforts, and at the same time we conduct those species-specific studies so that we very clearly understand how the Alaska environment and the Alaska ecosystem is going to respond in the face of not just ocean acidification, but in response to all of the climate drivers and climate change scenarios that we're seeing.
And one kind of clarify something. Just to clarify something, so when you talk about the food web and the chain, are we talking about some species of plankton, for example, that might be affected by acidification?
That's exactly right. So at the base of the food web are these tiny, sometimes microscopic organisms that we often don't think of, but they are the grass that grows in the ocean that really starts the food web that leads up to the larger animals that we think of as commercial and subsistence fisheries. And there have been studies both in the laboratory and in the ocean now where we've found cases where some of those plankton species are showing negative responses to ocean acidification levels that we see today. And that will probably get worse as we go into the future and ocean acidification continues to progress. So that's why we've got to carefully measure and carefully understand how those species are responding to the environments that we're seeing today, which will inform us and be able to help us forecast how the ecosystems will change going into the future.
Do we have any additional questions?
Hi, Gloria Dickey, Independent. My question is for Tom. I was just wondering, can you elaborate on the thermal siphons that you mentioned and how those work to cool the permafrost?
Sure. So they are passive devices. It's essentially a pipe that you stick in the ground, and it has a radiator sticking up in the air. And then there's a heat transfer fluid. I think it often is something like carbon dioxide, actually. And the boiling point of the fluid is basically in between the temperature of the earth and the air. And as a consequence, in the wintertime, the liquid will sort of fall down into the pipe, and then it will become vaporized in the ground because it's too hot. And then the vapor goes up into the air, all within the pipe, into that radiator where it will condense because the air is cold in the wintertime, and then it becomes liquid and falls down. And that process of vaporizing of that heat transfer fluid in the ground cools off the soil and then actually transfers the heat into the air. And but that system, unfortunately, is only going to be active in the wintertime. And so what we're thinking is that we would supplement it. We would actually have a hybrid system. We would supplement it with a solar-based system. So then you'd have solar panels, maybe on the roofs of coastal communities, that would basically drive a cooling system for the soil that would be active in the summer. Does that make sense?
So can I ask a follow-up question to Tom, since I'm sitting here? So Tom, is this the same things we see on the pipeline that kept the pipeline from sinking?
Yes. And they are the very same thing, and so they're tried and true technology. They have not been tried as far as cooling coastal permafrost is concerned. So I've been talking to everyone who will listen to say that this is really a good idea in some cases, and we're trying to get some support to do more detailed studies. But our preliminary work shows that they can be effective in cooling the coastal permafrost quite a bit.
Can they be deployed at large scale enough to stabilize an entire coastline? I mean,
Sure, and the reason is, like, just so the Air Force has a number of facilities all along the north coast. I think the old DEW line, and they're suffering from coastal erosion. They've had to spend, I've heard, almost $100 million redeploying infrastructure because of the coastal erosion problem. So there's definitely an incentive to come up with a solution. All you'd really need to do is to have, like, say, a 10-meter wide bank of these siphons, and just to form a block against that heat transfer. You could have the solar panels, if you wanted to use solar panels, extending inland as far as you need to generate enough electricity to drive a cooling system. And so, in my early remarks, I said, well, coastal change is happening differently in different locations, and so this approach might not work in all locations, like where it's real extreme, but there's definitely a lot of places where this would really be effective, as long as it works out as far as economics is concerned.
Shady Igor Oliver with the Arctic Sounder out of Barrow and Kotzebue. So I have a bunch of questions, but I'll keep it at two. So for Jeremy, I'm curious if you could talk a little bit about deoxygenation in the Arctic and how that plays in with acidification. And then I also have a question for both of you about the 2007 and this year parallels, and sort of a chicken and egg question of what sort of starts those patterns that we have seen sort of coming back again this year, just like in 2007. What sort of gets the ball rolling on those up and down changes?
Sure, so I'll go first. So deoxygenation is a sister problem to ocean acidification, and it's caused by organic matter that decays in the water. So when we think of like a tree or something falling in the forest and it rots and it breaks down, so that process of rotting consumes oxygen. So when a plant grows, it creates oxygen. When it's broken down, it's an oxygen consumption process. So when plants bloom in the ocean, the same thing happens. They produce oxygen at the surface, but when the plants die, they sink to the bottom, they're broken down by bacteria, and that process consumes oxygen. So what we're seeing in the Arctic is very high rates of primary productivity in the summertime, and then as that biomass sinks to depth, it's respired, it consumes oxygen and produces CO2. So remember, CO2 is what's causing ocean acidification. So that production of CO2 from that breakdown of the organic matter drives the pH lower, it exacerbates ocean acidification in these regions, and it consumes the oxygen in a region. So any animals that are living down at that depth are then facing two negative drivers of their physiology. One, they've got this ocean acidification effect that they're dealing with, and two, now they're dealing with an oxygen or a lower oxygen environment. So it's a big deal in some places, like the Gulf of Mexico, that's very warm, that gets hot in the summertime, because as the temperature warms up, it gets harder for the water to hold the dissolved gas. So oxygen is just a gas that's dissolved in the ocean. So as the water warms up, the oxygen wants to come out of that solution, and it drives the oxygen concentrations lower. So that's why we have big fish kills in the Gulf of Mexico in the summertime. It's because the waters become hypoxic. There's not enough water for the fish to survive. Now that's never been a problem in the Arctic because the water is cold enough in the Arctic. Even in the summertime, the water temperature stays low enough that we don't see hypoxic conditions in the Arctic the way we do in the Gulf of Mexico. But because the water is warming up in the Arctic, based on what Igor was showing in his presentation, we do know that there is going to be an effect. There is going to be a deoxygenation effect in the Arctic, and so a species that's used to living at a certain dissolved oxygen level is now going to live at a different level because of that warming, and especially if productivity in the Arctic increases, which we think it will with the loss of ice and the warmer conditions that are going to exist in the Arctic now, productivity will increase. The biomass production at the surface will increase. So now you're dumping even more organic matter down into depth, which will drive the oxygen concentrations even lower. So it's a sister problem to ocean acidification. We don't think it's going to be as extreme as it is in other places around the U.S. and around the world, but it's certainly an issue that we'll also have to keep an eye on as we think about our monitoring systems in the Arctic. But great question.
So the second question, which I can try to restate, but I don't know if I'll do a very good job of it, is sort of, since we've seen these parallels between like the 2007 year and this year, I'm sort of wondering what sets the ball rolling on those types of ebbs and flows with the temperature and the ice and everything else.
Okay. So, actually, you raised a very hard question. We are trying to find the answer for that for years. So from my understanding, currently there is no clear answer for that. So the same question repeated for many years already. Because atmosphere dynamics, even ocean dynamics, is more complicated than thermodynamics. So it's a common understanding. So from my understanding, because with the increase of temperature or warming forced by greenhouse gas, so there's the changes of the temperature gradient. That's the driver of atmosphere currents and the weather system. So weather is mainly developed by, we call it the baroclinic instability. This originated due to the temperature gradient. So the warming climate, this temperature gradient has been modified. So the weather pattern can change a lot. So when the weather pattern changes, it can trigger other loop for interaction. Yeah. So for example, if there's a more storm coming to north, and then the sea ice surface air temperature may increase, like what I showed, and then got a retreat of the sea ice, and the retreated sea ice add other thermal force into the atmosphere that can drag the storms further north. That's a loop. That's an interactive loop. I believe for the pattern, anomalous pattern occurred in 2007 and this year is mainly from interaction between the nature weather system and the atmosphere circulation system with the greenhouse gas forced the temperature changes. Yeah. So we are still working on that. It's a really hard question. Yeah. So you have something to add?
Yeah, I would add that there's multiple players in this game, and one of them are associated with atmospheric anomalous state, including thermodynamics, air temperature, and dynamics circulation pattern. There is another big player, which is ocean, which carries a lot of heat from northern latitudes to high latitude regions. However, there is an emerging new player in this game, and this is the Arctic Ocean and Arctic itself with its local processes. What we see with ice cover in recent years. Recent observations based on new technologies tell us that the melt of ice is more accelerated from the bottom, not from the top. That means that openings in the ice cover produce more open water and absorb a lot of heat from atmosphere. And this heat is redistributed in the upper mixed layer of the ocean and delivered to the bottom of ice. That's how it works, this system. And this way for ice melt is more efficient than atmospheric direct melt. So more open water in the Arctic in recent years creates conditions for much more efficient melt of ice, accelerating the process. And this is really a local process for the Arctic. What we see now is that this process is accelerating. And we may expect that the local process associated with effects like I was telling about will be enhanced in the future. There are multiple evidences that feedbacks are accelerated in recent years. And we definitely see a lot of evidence of local processes affecting multiple components of the climate system.
There's one. Okay. There's one thing I would like to mention because the community could be different. So recently, in recent couple of years, there's a strong debate on one scientific question. You know, when Arctic sea ice retreated, so there is at the same time there are stream events occur not only over the Arctic Ocean, also in the mid-latitude. So there's two groups in climate community. They got a completely different opinion, different research results. There's a strong debate. That's the reason I say you raise a really hard question. So some groups found, okay, sea ice retreat, ocean warming cause a shift of maximum temperature gradients location. But the other group say, oh, we did not find the strong evidence because the observational record is still very short. So that's only a couple of decades. Yeah. So it's a cutting edge question, actually, scientifically. Thank you.
Thank you. We have a few online questions here. There's a question for Dr. Zhang about that December superstorm. Just to clarify, was it an increase of 7 degrees Fahrenheit and not Celsius?
It's a Celsius.
Okay. And following up, would you be surprised to see another record low sea ice minimum this year?
What I say is because of winter weather pattern and sea ice pattern is quite similar to 2007. What I say is if the weather pattern continually vary in the same way as in 2007, we may expect other low sea ice cover in this coming summer. Yeah.
I had a question for Igor Polyakov there. There's been a theory that's been kind of advanced lately that perhaps the warm water anomaly in the Northeast Pacific was perpetuated because of the absence of cooling of the Northeast Pacific, and one of the things that maybe contributed to that was perhaps warm water from the Arctic Ocean down through the Bering Sea. What's your view of that particular theory as far as the Arctic Ocean kind of perpetuating the anomaly or the blob, as it's been called?
Yeah, there is a big discussion on the role of the Arctic Ocean and the Arctic climate system as a whole on what's going on in the lower latitude regions. Of course, there are some theories that the Arctic has dramatic impact on what's going on in Siberia or Japan or in the lower states, considering the snowstorms. So we may expect that the Arctic region has certain mechanisms impacting the processes in the lower latitude regions and in the Bering Sea, for example. But there are other theories that question big impacts of Arctic processes on the lower latitude regions. So this, I agree with Xiangdong, there are more questions in all these theories than answers, and we need to work hard in order to address them. So my perspective is on this issue is that they definitely have evidence of impact of high latitude regions on what's going on in subarctic regions, and that's my view on the issue. Thank you.
We have another online question for Dr. Zhang and Dr. Polyakov. It seems like you've been tracking specific sources of warmth coming into the Arctic from the south. We hear a lot about how Arctic warming affects the lower latitudes, but is this now understood as a two-way phenomenon with southern warming affecting the Arctic?
Yeah, I just can repeat that more and more theories appeared trying to explain the effects of Arctic on lower latitude regions and vice versa. And there is multiple evidence now that we need to consider the Arctic as a part of the climate system. And you can basically trace the evolution of scientific knowledge and scientific approaches to this problem, considering the global numerical modeling. in the early history of numerical modeling of the global climate system, the Arctic was essentially ignored. And right now, the present-day climate models just cannot proceed without including Arctic at very fine resolution, at very high level of details of simulating ice, ocean, and atmosphere. And this is very expensive, but global climate centers, modeling centers really contribute to development of these modules in their models. So this is just one of the justifications of the role of the Arctic in the global climate system. But again, this is a coupled climate system, and we cannot separate one from another.
I've got for Dr. Zhang, could you please pronounce your name slowly for me? I'm not a Chinese speaker. So.
Okay. My name is Xiangdong Zhang.
Okay.
Yeah.
And my question was, I'm recalling to some research that I think you did a few years ago, and correct me if I'm wrong, because I'm probably remembering it incorrectly, but you kind of referred to the lack of sea ice cover in the Arctic in some way impacting the jet stream, which then kind of shifted the polar vortex, which was potentially responsible for some of the extreme weather events in the lower 48. Are you considering updating that study or considering using modeling while also incorporating the effects of the current sea ice minimum, or what may be the expected current sea ice minimum, plus the increased temperatures in the Northeast Pacific, and how that may further impact the jet stream and contribute to more extreme weather events down the lower 48?
That's a good question. Okay. I'm currently co-chair U.S. Clover working group. We are working on that because there is a strong debate for this question. We call the group of people together from both sides to try to fix the problem, to find a good answer. It's really good, hard question. So we look at the atmosphere circulation or weather pattern is so complicated. The different researchers look at these changes of the system from a different angle, different perspective. For example, when we look at the surface sea level pressure, the surface circulation represented by the sea level pressure pattern. So we can easily find through modern experiments and data analysis with the sea ice retreat or warmer Arctic, we can find, we call it negative Arctic oscillation. What does it mean? That means the Icelandic low is getting weaker, and the jet stream getting weaker, and then the polar cold air is easy to move southward to cause a cold winter. So that part has been showing in different studies. That's many studies already agree on that part. The jet stream is really hard part, even the polar vortex. So we published paper last year. We found when Barents Sea, Carthy Sea ice retreat, that can cause we call it a planetary wave. Propagate upward to the stratosphere and then reflected down to the surface. So there is a couple months time lag. So that then causes changes of surface temperature, cold temperature, because of the negative oscillation of the negative phase of Arctic oscillation. But currently, there's a strong debate about the jet stream. So the jet stream is very complicated. So this mainly is okay. Actually, the driving mechanism has not been that clear so far. So generally, we think it's maybe driven by eddies, atmosphere eddies like storms, right? If there's storm activity, that can enhance jet stream. So storm activity eddies can be from temperature gradients. But that part has been, research on that part has been not consistent among different research. Yeah. So it's a very complicated dynamics. Even, I got discussion in this meeting with a number of people. So currently even some atmosphere people, the atmosphere scientists think, oh, dynamics is just a random behavior. We can simply treat it as random. Yeah, I don't think so. We try to find a signal from a noise. Yeah, this is still a working question. Yeah. Okay, hopefully we get an answer very soon. Thank you.
Do we have any other questions? Okay, all right. Okay, thanks everyone. If there are any follow-up questions after the fact, you can send them to Marmy and Grimes at ASSW2016/news/media. Thanks to the panelists and thanks to everyone who participated in these briefings this week.
Thank you, everybody.
Okay, thank you.
Good job, guys.
Generating
Oh, thank you.
projections of sea ice and